Thank you for attending. In this session, we'll discuss a new framework. Thank you. We'll discuss a new framework for NetBSD Kernel that I have been working on recently. The purpose of the framework is let your NetBSD bots run as USB devices, such as printers, USB serial, mass storage, or Ethernet adapters like that. In USB, there are two roles: the host and the devices. And host size, NetBSD kernel have been supported host side USB very long years. And now our framework supports this side. Okay. At first, I'll give you a very quick overview of USB systems for a discussion. It's very briefly. Of course, some of you are very familiar with it already, so please be patient. This is USB bus. There is one host and many devices. And the devices have addresses that are assigned by the host. And to make a tree-like topology like this, you use a USB hub here. From the viewpoint of the USB devices, the hub is transparent, so we can forget the hub for this discussion. Okay. This is a physical connection between device and upstream. Data goes through these two lines called D plus and D minus. And device checks this reverse line to detect the host. And the host checks this D line to detect the device. Device can control this pull down register. So device can disconnect it from the host by turning off this register without actually unplugging the cable. And this is a logical connection between device and the host. Device has data ports named endpoints. They can have up to 16 endpoints in a device. And data pass from the host to device's endpoint is called pipe. And the pipe to the endpoint number 0 is very special and called control pipe. That is used for enumeration and configuration of the USB devices. Okay. Usually, USB device has only one interface in it, but sometimes it can have many interfaces in the device. And this type of device is called composite device. One of the design goals of our framework is to offer a very easy way to make a composite device like this. Okay, and for device to show the logical structure like this to the host, device has a data called USB descriptors. Descriptors has a format like this. It has a device descriptor and there are IDs to identify that device. And in the descriptor, device descriptor, they have a configuration descriptor, and the configuration descriptor has an interface descriptors. And in turn, in the interface descriptor, they have an endpoint descriptor, so that which endpoint is used for which interfaces. So it is one of the jobs that framework needs to do is to maintain this descriptor to show it to a host. Device descriptors is defined in the USB specification, so please refer it for detail. Okay, I'll skip this page and next page and finish a brief explanation for USB system. And now goes to our frameworks. Okay, design goals. First, common tasks among many USB devices should be done in the framework. That is those separate implementations. After all, that's the purpose of any framework in the world. So this is a very natural goal for framework. And the framework itself and implementation USB interface should be independent. I mean, machine independent to the underlying USB client controllers. So if you write interface implementation for example, Raspberry Pi, it is expected to work on the other platform like MIPS Space SOC or x86 based SOCs. And next goal of is interface can be implemented either as an in-kernel device driver or a user canvas. So if you use this user programs, when you start that like a demo, it will provide functionality of USB devices. Like this. I'm sorry. Here I want to discuss another design goal. Okay, we want to implement like this way. Okay, I'm sorry. The device can transform into another device without rebooting the NetBSD kernel into another kernel binary. So when at first, for example, start as a USB camera and connect to the PC, and it can transform to another USB device like USB mass storage without rebooting the kernel inside of that box. And the USB specification doesn't define that kind of transforming. For example, if once the USB camera is connected to the PC side never expects that the camera eventually transforms into a printer. So we need that track to implement that transformation feature. Okay, this can be last. Last design goal is okay. This one. This framework can be used to implement a very simple one interface device, and that interface can be used to make a compound composite USB devices. So we want to make it easy to build a composite USB devices. Okay. So considering those design goals, we put those subcomponents in USB framework. And one is called usbp. This is the main. This is the main part of this framework, and do very basic things like enabulation and configuration. And it controls, maintains the control types. And another one is client controller drivers. There are many controller drivers in the market, and every SOC makers have its own designed client controllers. So you need to write drivers for them. And the USB interface drivers provides functionality as a USB function devices. Then we have a user interface to USBP from Userland, so that this Userland program can act as a USB device. This is a relation between those subcomponents. You have USBP here. This is control the entire framework. And if you want a new USB device, develop a new USB devices using a NetBSD, you write this interface drivers or Userland program to provide that functionality. And if you want to port this framework to another platform, you need to write this part, client controller driver. So anyway, we already have this part, so this porting should be easy. Okay, I already explained this, so I'll skip this. Okay, so let's see how we combine those subcomponents into a kernel. This is our config file. At first, you have a client controller driver here, and attach the USB-P to that driver, controller driver. And on top of that USB-P, you attach many interface drivers. In this example, you have a Ethernet emulation driver and a USB serial emulation driver here. Very interesting point of this is you can use UCOM here. UCOM is a driver for USB serial. That is a machine independent part of a USB serial. That is designed for host side USB. And now we can use that UCOM for peripheral side without any modification into UCOM. That is very interesting part of this. And another one is this is a Userland gateway for USB-P, so that Userland program can access to it. Okay. In that configuration, we had two interface drivers attached to the USB-P. You can attach any number of interface drivers to USB-P. Some of drivers cannot go into the device because some limitations. In the ideal world, any number of interfaces go into that composite devices without any trouble. But in real world, there are many restrictions that because of that you cannot use this interface in this composite devices. Some of these reasons are number of endpoints or client controllers limitations, and interface wants to use a control pipe exclusively, and it can't share it with other interfaces. I wrote a little bit in more detail about that limitation in my paper, so please refer to it. Okay, so when an interface attached to USB-P, interface may not be going to the device configured. So interface needs to know if it was actually configured in that device or not. Okay, so this is an API to add USB interface to a USB-P. please note that this API is, I'm debugging that now very heavily, so it will modify in future. Actually, I changed this last night, and it is already modified from the version in my paper. Okay. You give a device object here so that you can attach the interface to that device. And in second argument, you give information about your interface, like what is the ID of your interface, or what kind of that, like that. And the third one is a table of methods that interface provides to usbp. And finally, you get the interface object in this last parameter. And this second parameter, this is actually a really big structure. And it consists of 3 parts. First one is information about the device descriptor, like a device ID, vendor ID, product ID, like that. And the second one is a characteristic of an interface. It also has IDs for interface and then the number of endpoints that it requires. And third one is a specification of the endpoints that interface requires, like it needs 2 bulbs and 1 interrupt pipe, like that. Okay, this is a device information you provide in the framework. Okay. All interfaces that attach to usbp will provide this information. But in the device instance, we have only one place to put this. So our framework pick one of these interfaces from many interfaces and use it. Okay, this is information about the interface itself. Here is the IDs and description string for interface. And this one is how it uses the control pipe. So some interface doesn't use control pipe at all, and some interface use control pipe that can be shared among interfaces. In that way, shared among interfaces. And some interface use control pipe its own way. So if the interface uses the control pipe in that way, that interface cannot be combined into one device with other interfaces. And finally, you need to specify a number of endpoints you want to use for that interface. You specify endpoints like this, direction, in or out, and type of the transfer, like bulk, isochronous, and interrupt. Currently, we only support only bulk transfer. In the future, we will support isochronous and interrupt. And you can explicitly specify the endpoint number, like that interface want to use endpoint number 2 and 4. It is possible not to recommend it because USB client controller has its own limitation about the usage of endpoints. So if you specify the number explicitly, it may not fit to the client controller. So we recommend you leave this to 0 here and let the platform framework select the endpoint number. And you can say this request, endpoint request, optional. So if the client controller doesn't have that endpoint, or that endpoint is already used other interfaces, you can run that interface without that endpoints. In that case, you can set this mark that is optional. if you don't mark that optional, and you can, framework can't provide the requested endpoints, that interface are not going to that device. Okay. And you can specify a packet size for the endpoints. And if we support isochronous transfer, we'll need more parameter from here. Okay, this is a method table. The interface implementation provides to usbp. Important thing is this configured method and unconfigured method. As I already told you, interface need to know if it was actually going to the device or not. So this method is called when it goes into the device actually. And when the other interface attached to the usbp, sometimes your interface may be extracted or kicked out from that device. In that case, the unconfigured method is called. So when you write attach the interface driver to the usbp, example sequences will be like this. This is the example sequence for a kernel startup time. Kernel attaches to the usbp, and the usbp search is it's a child drivers for interfaces. And the interface is called that API in attach routine. So here are the two interfaces, and they both call the interface this API to add the interface to device. And after that, usbp will build a USB device actually from the list of interfaces attached to it, and then select some of interfaces that actually go into the device. In this case, interface number 1 is succeeded to go into the device, but interface 2 are not selected. So configured method is called to this interface only. After that, this interface starts to act as a USB functionality. So they open the pipe and begin to send or receive packets on the USB wires. Okay, here's an example list of other APIs. Of course, we have a delete interface API, and other interfaces, other APIs, like start API that starts with usbp is provided by this usbp framework. And also we use a usbd something. This is a function for host side USB. So sending or receiving packets, we use host side calls for peripheral sides. This is why the UCOM driver could be used without modification for both a host side and a peripheral side. Okay. Next one is how to use that framework from Userland programs. We'll have a device node named like this. I'm not sure everyone likes this name convention, but currently I do it in this way. So first we open this control device of the USB and issue this I/O controller. This I/O controller, the interface I/O controller is to call the interface API in the kernel based on the information provided from the Userland program. And then the Userland program called this get endpoint I/O controller, so that to know the actual endpoint number that are assigned to the interface. And this call will be blocked until that interface is actually going to the device and configure. And once you get the endpoint, actually, you can open these endpoint nodes for endpoints based on the endpoint number. And reading or writing those device node means you read or write the endpoints, actually. This is how our Userland program runs for implementing the USB device function. Okay. Current implementation is stored in the GitHub on this URL. I put the only file that I modified for that. So if you want to use this, you need a NetBSD kernel base and add this file from this Git on the edge and merge it and compare it. Okay. But now I'm still debugging and making a new feature on this. So, maybe it's not wise to try it now. Okay. I started this project by porting OpenBSD codes to NetBSD. OpenBSD had since very many long years, like I don't remember, but many years ago, they have a US code driver called usbp. This is the main part of the peripheral support on OpenBSD. And OpenBSD has only one interface, USB device interface. It is a CDC Ethernet emulation driver. Reason that OpenBSD guys wrote it, I guess, is others use it. So OpenBSD people wanted to use that Ethernet emulation on USB to communicate with the PC on towers. And OpenBSD has never enhanced or adding new USB devices on it. So I guess that USB framework is not so well welcomed in our OpenBSD package. Okay, Linux also has support for peripheral side of the USB for many years, like kernel 2.4 era or something. It is called gadget in the Linux world. I haven't studied that gadget things very closely yet, so I can't say anything in detail about gadget. But as far as I read the website and codes, the feature provided by gadget is very similar to our design goal. I didn't find yet a big difference between ours, ours in the future and Linux in the implementation. Of course, there are many steps ahead of us, so I think we need to catch up with them by providing more functionality in this area. Oh. Okay. Okay, I'd like to show some demonstration about our framework here. Okay, this screen is a console output from this notebook. So you can see the USB device already connected to this PC. And this output is a console output from this evaluation board. The usbp frameworks running on this board. And this is a normal terminal running on this node. So, okay. This is the evaluation board running on. Okay. This kernel is configured that configuration file I show you in this presentation. So it has a client controller here and a USBP driver here, and we attach the CDC Ethernet emulation driver and FTDI serial emulation. And the FTDI has a Ucon on it. And finally, we have a Userland here. So, and from the host side, we see the this is the USB device that is provided by our framework from this platform, emulating FTDI here. So this is a USB serial. Yeah. So now that this board is playing as a USB serial now, so we can tip on it. Yeah, we connected. Can you see this? This one, bottom right. And we can send some characters from here, from the board. Right. Like that. And close the clip here. Okay. As you can see, we have two interface drivers. This Ethernet emulation and USB serial emulation on that USBP. But from the host side, only the USB serial emulation is seen, because this FTDI emulation driver wants to use a control pipe exclusively. So there's no room for this CDCF driver to go into the device. So now we detach that FTDI emulation driver from the tree, like this. You can do this by unloading a kernel module, but here drive control can be used for that purpose. Okay, now that USB serial emulation driver is gone from that USBP. So now USBP recreate the device using remaining the interface drivers. In this case, here now CDCE, that is a Ethernet emulation driver, come into the device actually. So now in this, from the host side, you have a CDC interface, network interface here. This is actually USB devices on that platform. Okay, so now we can. On the platform side, we have a CDC-F interface like this. So we can ping to that. Okay, now we are sending return packet over the USB line using that framework on that platform. Okay. And now third demonstration, and the last one is run a Userland program to provide a USB device functionality. But it's not completed yet, so it doesn't actually read or write packets on the USB wire, but at least it can be used to make a USB descriptor. So I run the UMass daemon on that platform. Actually, if finally I completed this program, I will give a file name or device name that we can use the storage for that USB mass storage devices. But currently we don't have it now. Okay. When I started that UMass daemon, here's you have a UMass is detected from the host here, and the CDC is still there. So you must also use a control pipe, but it uses a way that can be shared on interfaces. So CDCF can share the control pipes with the UMass. So those two interfaces go into the device, making complex devices. So now, from the host side, you see the here you have that device provided by our framework. Has two drivers on that device. This is a host side detect that is a composite device, and load the two drivers here. So in this framework, just by adding or deleting the interface driver, you can make a composite device very easy. Bad news is, for example, this. Even if we can easily make a composite devices like this, host side may not treat that very wisely. For example, current implementation of CDC driver doesn't suppose that this CDC emulation, Internet emulation comes in a composite devices. So it's just currently it doesn't work in this way. Okay. That's all for my demonstration for now. Okay, so let's go back to Okay. Things to be done in the future. Okay. Of course, I need to clean up my codes and get reviewed by the developers and commit it into our code base. And we need more controller drivers. I will start next week for a new some evaluation boards like what one? Beagle or Wonderboard or something like that, or Raspberry Pi. Modern embedded platforms usually have that USB device support. So we have a lot of platforms that we can run this framework on them. And of course, we need more interface drivers to provide USB functionality, like PTP devices and mass storage I'm currently working on, and audio, video, like that. Gadget, Linux gadget already have many USB functionalities, so maybe we can see that what kind of USB functionality is useful in the market. Okay, and we need a DMA support, currently not supported. And the USB controller currently supported works on a USB 1.1 specification. So I haven't tried 2.0 devices. As far as I know, 2.0 needs one more additional USB descriptor. Other than that, probably the USB controller takes care of it. So this will not be a very difficult thing. And of course, we want a 3.0. And I'm not familiar with USB 3.0 yet, but I know that one more descriptor we need for this. So there are lots of work to be done. So anyway, I need to clean up code and get push it to the code base so that anyone can help this. Okay, questions?
I think we have discussed it before, but what is the major motivation of of this development of yourself?
For myself, it's very nice to increase the number of ways to make a communication between embedded platform and the PCs. You may have an Ethernet or SD cards or something like that, but sometimes there is no usable communications on your developing platforms, except the USB device side. So if we have this framework, you can use it as a serial console or network interfaces. So it will increase the usability of your platform as a hardware for NetBSD. So this is a very big motivation. Okay. I thought. Finally, I'd like to thank these guys for helping me. Thank you very much.